Assalamu alaikum. This is Rafi Mustafa Kamal introducing our project for the Chemical Process Control course on the behalf of Group 1. So essentially, we wanted to create a temperature control model because personally we feel like it's one of the most fundamental challenges that we face on a day-to-day basis, whether be it something as simple as controlling the climate of the room or keeping our CPUs away from melting in the first place in a computer system. So for the scope of our project, we essentially wanted to model an SSC auditorium, and we made the use of an acrylic box in order to do so. And what we are essentially trying to control over here, or what we are trying to achieve over here, is to make sure that the temperature inside the acrylic box remains at a steady state. So for the scope of this project, our control variable is going to be the temperature inside the acrylic box. Now if I talk about the manipulative variables, these are essentially the levers that we are pulling, or our ways of trying to manipulate the temperature so that it remains at the steady state, provided that there is any disturbance that is introduced. So we are using this by making a use of the PWM signal, which is essentially either trying to raise the temperature if the disturbance is causing the temperature to lower down in the acrylic box, or we are trying to lower the temperature provided that the disturbance has caused the temperature to rise up in the first place. When I talk about the disturbance variables, for the scope of this project, we have essentially considered the ambient temperature that exists outside our acrylic box to be a disturbance variable, with heat transfer existing in the form of convection, conduction, and radiation. Now Aisha and Maliha would be breaking down the functionality of the project.
So I'm going to walk you guys through the model and the logic that I use behind this. So this box over here is what I've used to sort of model like one of the auditoriums in SCC. So if you look at this side, this is a ventilation space for the fan, and this is like a removable top lid that we have in order to introduce disturbances in the system. So all of this is the logic that goes into the circuit. So over here we have an Arduino, right? And the Arduino is going to take the signal, the digital signal from these two temperature sensors. So this and this, these two are the temperature sensors that we've used. These are the DHT11 temperature sensors, and what these temperature sensors are doing, they're taking an average of the temperature, and that temperature, that digital signal is going into the Arduino. The Arduino is then connected to the motor driver, and that is what's going to amplify the signal. The motor driver over here, one side of that is connected to the fan, and the other side is connected to the halogen bulb, which is the heating element that we've used. So if the current temperature of the room goes below the set point, we want heating, so the bulb is going to turn on. And if the current temperature goes above the set point, then the fan, which is our cooling mechanism, is going to turn on, and the fan has ice over here to like make the air that it releases cooler. And that's pretty much it.
Okay, so our system is basically using a PID control, which stands for proportional, integral, and derivative. And the results of this you can see are being shown on this graph, which is logging the real-time results of our system. Now, what the PID control does is that the proportional part of it is controlling you're getting your error right, and your sensors are measuring that error and it's comparing it to the set point temperature. And once you get that difference between the set point temperature and the actual temperature, you get the error. The proportional control looks at this error and gives you an output, a control output according to proportional to that error. The integral control then comes in, and what it does is it logs all of the error from the past and gives you a cumulative result from that error to minimize any sort of fluctuations and to get rid of a steady state error that you would have gotten with the proportional control. And the derivative control then comes in, and what it's doing is that it's looking at the rate of change of the error in the past, and it's predicting कि आगे क्या आपका error बनेगा, and it's controlling that, and that helps make it more stable. So you can see our system right now is quite stable. It's running at a set point temperature of 25, which can be seen on one of these lines, and you can see our actual temperature is very, very close to that. See, our actual temperature is 26.7 while the set point is 25, and this is a result of What is, yes, our fan temperature right now, which you can fan right now, which is working at a power of about 255. This is our bulb which is turned off because we don't need heating right now, we need cooling. If I were to change this, you can see if I increase the temperature, then you can see here the fan's power output goes down, right? And still going down, 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 because it's still, right? This is the fan, it's fluctuating according to what we need. And if I increase it a little more, because if I want heating, look, the fan power went completely to zero while the bulb power rises and fluctuates according to what your actual control output is doing right now. So you can see the temperature is also rising over here.
Okay, so this LCD display over here actually tells you the current temperature of the room and the set point temperature, and this also shows you the power that is given to the bulb and the fan. So if I change the set point from 30 to, let's say, 25, then the fan should turn on. Why is that? Because the current temperature is higher than the set point. So in order for the system to lower the current temperature of the room to the set point, it requires cooling, and hence the fan turns on. And you can move to that side and see for yourself that the fan is turned on. And over here on this PC, we have the real-time logging of how the fan speed and the bulb power changes as the set point is varied and as the current temperature approaches the set point. I can show you a bit of variation on this by just changing the set point. Let's say I increase it back to 30. Okay, so you can see the variation over here. And this is what actually tells me that there's been a disturbance in the system, or like a change in the set point. Okay, so as can be seen from the LCD display, the current temperature that is measured by the temperature sensors inside the box is 28.5 degrees Celsius, and the set point is 21 degrees Celsius. Since the set point is lower than the current temperature inside the box, the system requires cooling, which is why the fan is operating at its maximum PWM signal of 255. Now, if I were to increase the set point from, let's say, 21 to 25 degrees Celsius, let's see what happens. Okay, so as you can see from the LCD display, as well as from the PC that is logging the data in real time, the fan output went down from 255 to a certain value, and then it went back up to 255, which shows that this system indeed incorporates modulation. Now, if I were to further increase the set point from 25 degrees Celsius to 30 degrees Celsius, let's see what that does. Okay, so as you can see, the fan PWM has gone from 255 down to 0. And since the set point is now higher than the current temperature of the room, the system requires heating, which is why the bulb PWM has increased from 0, and it keeps on increasing.
As Aisha successfully demonstrated in the last clip, we were able to execute the project, and our temperature sensors were able to log in the real-time data, which was then embedded into the Arduino code to present a graph which showed the fluctuations of how temperature is changing in real time. So overall, this project was a success from our side. Thank you so much.